I think in the middle of the talk, I'll keep one stopping point just in case there are questions that someone watching on YouTube has. So please feel free to ask, and we'll get to those questions either in between the talk or at the end of it. And again, sort of teaching at your own fun. If there are some technical issues, please feel free to interrupt and let me know, and yeah, we can figure things out. Yeah, with that, I guess I'll get started. So yeah, today I wanted to talk about trying to reconstruct everyday objects in 3D. So essentially, we want to build some approaches or systems that can reconstruct over tens of thousands of object categories that exist in the world. And just to show 3 specific examples among those systems that can pretty accurately reconstruct the 3D shape of things like the monitors or bagels or fire hydrants and other commonplace things that surround you. And sort of maybe taking a step back from objects, a very long-standing goal in computer vision has been to make inferences about what we see in an image. So for instance, if we take an image such as this one, then the state-of-the-art computer vision systems are very good at making 2D inferences. So for example, mass Gaussian that you can take from off the shelf very accurately and very quickly detects some of these objects, demarcates even the pixels corresponding to the chairs, the couch, and even some of the books that you see on the right. And while this 2D understanding in terms of labeling pixels is great, it only reveals some aspect of the world. What it sort of misses is that this particular image that we are seeing, this sort of 2D representation, is in some sense just a window to the actual 3D physical world behind it. In some sense, this image is just a painting that depicts the underlying physical spatial world. And if there's sort of any agent or a robot that is seeing this image, it doesn't really care about the pixels of this image. What it really cares about is this underlying spatial world behind it, because that's the world that this robot will operate in. It will move around. It will probably go and grasp the cup and probably bring you water. So while this 2D understanding is great and is applicable for many scenarios, what my interests lie on are how we can get to this understanding of the underlying spatial world that is behind this image. So sort of more concretely, the overarching goal of that motivates what I'm going to talk about today is, given just one image of a scene, or maybe a very small number of images of a scene, we want to infer a spatial 3D representation of the underlying world in that scene. And while this is sort of a very challenging task, some of you who may be just very cursorily familiar with some of the successes in computer vision might be wondering why this is a challenge. For example, maybe you're familiar with some remarkable results from even actually a couple of decades back, where we've shown that we have systems that can very accurately reconstruct entire cities. And I'm just talking of a specific room. And we have, for instance, the system from Noah Snavely, which can look at images from a lot of tourists and reconstruct the Roman Colosseum, or actually in some follow-up works, reconstruct other landmarks and even entire cities. And similarly, we have had, again, from a few decades, systems that, given a few images, for instance, of the statue, can very accurately get a detailed 3D model of this particular object. For example, this work from Carlos Hernandez et al. And some of these systems are also used to reconstruct other objects of interest, such as sitting presidents, where this image is courtesy Paul Debevec, where they have this dedicated scanning system which can capture a very rich and detailed 3D structure of President Obama. And so it's kind of clear that towards this goal that I mentioned of being able to infer the 3D structure, we have made a remarkable amount of progress, and all of these results that I'm showing here are examples of the impressive success we've made over the past few decades. And so why is it that sort of the problem that I'm talking about is challenging? And to sort of better motivate that, I want to just lay down the landscape of what I think the 3D inference, so the task of 3D inference, and look at a few of the approaches that we saw in context of this landscape. So one axis that I really want to emphasize is that of ease of inference. So if there's a new object that we wish to recover the 3D structure of, this axis sort of characterizes how much effort you as a user have to put in to get the 3D of that new object. So for example, on the left hand is if you have to build really a dedicated scanning setup or capture hundreds of thousands of images for this particular instance that you are interested in scanning, then that's something really difficult, and it's a lot of effort to get 3D for one specific instance. And sort of on the other extreme of this ease of inference is that if we can perform 3D inference from just a single image in the wild, I just see an object and casually capture a single image of it. And if that is sufficient to give me an accurate 3D model of it, then that's something that's extremely easy to use. And the inference for a new object that we're interested in becomes really, really simple. And some of the early approaches, for example, that we saw, while being sort of very generic, are a bit more difficult to apply, whereas some of the single view reconstruction methods, as this axis illustrates, might be a bit easier to apply for new objects. But of course, there's this complementary axis that we're also interested in, which is sort of what I started the talk by, that we want a system that can reconstruct the everyday objects around it. And essentially, by some estimates, there are these over 10,000 object categories in the world. And with maybe just that rough number in mind, the question of generality boils down to, if we take a system, then how many categories amongst these 10K categories is this system capable of reconstructing? And sort of on the one hand, we have these very general multi-view stereo or structure from motion-based approaches, which really are general, and assuming we can capture the sort of data they require, they don't really have any constraints in the kinds of scenes or objects they can model, and can really work across arbitrary objects such as the statue here. And sort of on the other extreme would be some very category-specific models, such as ones that infer very detailed 3D structure of faces, perhaps even just from single images, but are of course limited in their applicability in that these developed systems only function on a very, very small set of categories. And so this is sort of the landscape that I want to emphasize today, which is we want to develop systems that are ideally both general and work across a broad set of categories, while also being able to easily apply them to novel objects that we are interested in scanning. And with that, I think we can characterize how the landscape of 3D reconstruction works over the decades has looked, actually starting from some of the classical structure from motion or multi-view stereo approaches, which really, while being really, really general, are a bit harder to apply for novel scenes because they require either a dedicated capture setup or require at least hundreds or thousands of images of the specific scene that we are interested in reconstructing. And actually, on the other extreme, interestingly, is the very first computer vision thesis by Larry Roberts, which was performing the task of single view reconstruction, but in a very specific setup where there were some assumptions about the world that it comprises of simple things like cuboids and pyramids. And given that assumption, it could infer 3D structure from a single image, but of course is limited in its expressivity and generality because of the fundamental assumptions made about the possible variation allowed. And sort of over the next few decades, we did make a few strides across both of these tasks. So for example, model-based detection or model-based 3D detection methods, where I'm just highlighting some seminal ones, but of course there were several hundreds of these, expanded our capability to reconstruct a larger set of categories, though some of the initial attempts actually required some test time annotations, such as knowledge of a template or knowledge of key points, and so were a bit harder to apply, but could let us go from these very toyish block world settings to being able to reconstruct about 5 to 10 object categories, such as cars and airplanes and faces, for example. And sort of with the advent of more deep learning, we again built systems that push this generality boundary a bit more. For example, initial work by Rohit Girdhar et al., which could reconstruct some of the furniture items, and some more recent examples such as mesh ASEAN and some of our work which could reconstruct birds. And these systems allowed us to push the boundary on the number of categories that we could reconstruct. But some of these earlier attempts still relied on either ground truth 3D supervision or key point supervision or camera pose supervision, and could not still scale to the tens of thousands of categories that we sort of ideally want. And in parallel, I think we have more recently made very impressive advances in, again, pushing the boundary of multi-view reconstruction and getting far more detailed reconstructions. For example, this work from Ben Mildenhall et al., Nerf, which I assume everyone is familiar with, where the system could get really accurate and detailed 3D reconstructions given a few hundred images. And some later approaches have actually pushed the boundaries of it by possibly reducing the requirement of the number of images or relaxing the requirement of very precise camera poses, such as the one from Lin et al. And so in some sense, these pushed the boundary of multi-view reconstruction works and made inference easier by some degree by allowing only approximate camera poses or a slightly fewer set of images. But still being very far off from the other extreme where we can infer 3D from just a single image. And sort of to emphasize again, the gold standard or sort of the ideal point that we are striving for is something that's extremely general, can work across tens of thousands of objects, while only requiring, let's say, just a single image to make such an inference. And while in this talk, I'll unfortunately not be able to present to you a system that gets to that, I think this talk will focus on pushing the boundary from both directions. And in particular, I'll talk about one work which pushes the boundary in terms of number of categories that we can reconstruct. So for example, going from about 10, 15 categories that prior works could reconstruct to something around 100 to 200 object categories by presenting a more scalable approach for learning from image collections. And secondly, I'll talk about an upcoming paper at NeurIPS where we push the boundary in terms of relaxing the number of viewpoints required from, say, 50 to 100 images of an object to be able to reconstruct objects in 3D given a very small number of images, such as just 6 or 8 images that perhaps you might capture if, let's say, you want to sell your product in a marketplace setting. And first I want to focus on this work, which pushes the boundary of single view reconstruction. And this work was actually led by Yufei, who's a PhD student at CMU and was in collaboration with Abhinav. And actually, I'll very briefly also talk about a follow-up work that Kalyan, who's at Facebook, was leading, where we were trying to extend this initial work to sort of improve the quality and scalability a bit more. And so before going to the work, I was sort of making this point that the existing reconstruction systems, for example, supervised mesh prediction systems or key point supervised bird 3D prediction systems, are still limited in their generality. We have these systems which typically have been applied to reconstruct around tens of object categories, but this is still a far cry from thousands of object categories that sort of really surround us. And this is actually in stark contrast to what we have seen in object recognition, where, let's say, given the Elvis dataset, that this is an image from the Elvis dataset, we really have systems which can detect and segment very generic objects in the wild in challenging image settings. So this particular image is actually an annotated ground truth and not a prediction, but the prediction systems that use this dataset and are actually not very far off from being able to produce detections that are of the similar quality. And so while we have made huge strides in having more general recognition systems, I'd argue that we have not made similar strides in having similarly general 3D reconstruction systems. And the reason why this is hard, or the reason why there's this difference between progress in recognition and progress in 3D, is that 3D annotation, which is what typical supervised learning approaches rely on, is extremely expensive or difficult to acquire. So this is, I think, a video from one of, probably the leading 3D annotation datasets from 2014 called Pascal 3D, where we are visualizing the annotation process that a specific Turker has to do to annotate 3D for a single object that's visible in this image. And it's actually quite tedious. This requires someone to select an approximate 3D model and then carefully align it with this particular image. And even then, the best we can hope to get is just some approximate 3D structure and not really the true 3D structure, because we're just selecting an approximate 3D model from a library. And to make this efficient, that library cannot be too big. And at best, we can only hope to get an approximate 3D structure aligned. Despite sort of a lot of effort. For example, it takes a few minutes to, over a minute to annotate one particular instance. And sort of in contrast, process of 2D annotation, which is drawing 2D bounding boxes, or maybe just drawing code segmentation masks, is extremely efficient and extremely fast, and is much more scalable than having to rely on 3D annotations. And so sort of with this in mind, I think it's rather clear that if we want to have systems that are scalable and can learn 3D reconstruction for a broad set of categories, we should not really rely on sort of strong 3D supervision for learning. And I mean, in fact, this is not anything new. This idea that we should be able to learn 3D without requiring direct 3D supervision has actually been explored in the community over the last 5 to 6 years. And some of the common alternate forms of supervision that people have been relying on is, instead of assuming 3D supervision is available, we can assume multiple views of the same object are available. So for example, 2 views of each chair are available, and that allows us to learn 3D because we can predict 3D from one view and verify it against another view. Or for example, we can assume that an approximate 3D template of a category is available, and that really guides the process of learning 3D from image collections, because the availability of template lets us constrain the amount of variation we allow. Or for example, even if multi-view images are not available, one can rely on knowing the precise camera pose for a particular image with respect to some canonical space. And knowing this camera pose, again, sort of simplifies and regularizes the process of learning 3D. And an alternate to using camera pose is one can use some semantic key points being annotated. And this is also indicative of camera pose while giving some additional fine-grained detail as well. And this can also guide the process of learning 3D from these image collections. But all of these approaches that I'm highlighting here, while they can learn 3D without 3D supervision, do still require some additional annotation, either in the form of templates or semantic key points or camera poses. And this, again, restricts their scalability in a practical setting where, let's say, if we are interested in getting 3D reconstruction across all of ImageNet, even these annotations or this form of supervision is not easily available. So what I'd argue is, and so maybe just to highlight this point, for categories such as leopards or vacuum cleaners, or more generic ones like shelves or things like bagels, each of these assumptions of requiring camera poses or having a specific template that captures the variation or having sort of multiple images is not really something that's very practically applicable. And so ideally we should be able to learn 3D prediction in an even more generic and scalable way that does not even rely on any of these annotations. And so more concretely, the form of annotations that we look at is just using foreground masks. And so, for example, this is us browsing through this data set called Open Images, which has these sort of user-guided, semi-automated annotations. But then given these segmentations, we can actually just learn a segmentation system that can give us coarse foreground masks for any object among these categories. And the knowledge of image collections with just foreground masks is something that's very scalably achievable. And we want to look at learning 3D using just these annotated image collections. Just these image collections with only foreground mask supervision and no other annotations. And sort of more concretely, the task that we are interested in is what we call learning 3D via shelf supervision, where it's just a fun play on the fact that we use shelf supervised off-the-shelf systems to provide supervisory signal. But the setup that we're interested in is, given a single image, we want to have a model that can infer the 3D shape and camera pose. But as training signal, all we are relying on are these image collections with foreground mask annotations without any additional supervision for templates of the category or for camera pose or key points that some of the prior works assumed. And of course, this is a very challenging setup to learn from because, as I said, there's no direct 3D supervisory signal in this training data. And to allow learning from these segmented image collections, we propose an objective that actually just combines 2 terms. First, we just say that this prediction system that we are learning, which predicts the shape and pose, should be consistent with the original input image. So we have this predicted shape and a predicted camera, and we say that this shape, when rendered from the predicted camera, should match the input image as best as possible. The second objective, which prevents some degenerate possible solutions, simply says that this particular shape that we predicted, when rendered from a novel viewpoint, should look realistic, whether a rendering is realistic or not can be judged, as I'll describe in a bit, through some adversarial network that is trained on a lot of real images of birds to tell it what real images look like. And just using these two objectives can allow us to learn 3D prediction by simply saying that the predictions should match the input and they should look realistic from arbitrary viewpoints. And I actually like to really note that this approach was motivated by some prior papers which also use similar insights, in particular, this Hologan paper, which really showed the power of these adversarial constraints, and similar work from Hensler et al., which also highlighted the power of these adversarial constraints to allow learning efficient 3D. But some of what I'll talk about today really looks at scaling these ideas and incorporating more geometry in the rendering process. And sort of in particular, what we infer from an image is a sort of two-stage representation. So given an input image, we first predict a camera viewpoint and a shape in a volumetric representation. And then we specialize it to better match this particular instance by converting it to a mesh and optimizing it to match the details better. And sort of focusing a bit more on the first part, this volumetric representation that we infer, this shape S, actually has two components. It has a shape S in the form of an occupancy grid and a voxel grid, and also features associated with each of those voxels. So one can think of this as a semi-implicit representation where an explicit occupancy for each voxel is represented, but also sort of an implicit feature is represented to allow capturing the appearance and some other fine-grained geometry if needed. And given this representation, we design sort of a differentiable renderer, following some of our previous work on how to do ray matching in a probabilistic occupancy grid. But this differentiable renderer essentially can, given a query ray, aggregate the feature along that ray by accounting for the occupancy of the voxels along this and do some sort of occlusion reasoning. And I'll really skip the details here, but essentially this differentiable renderer can aggregate the features along a ray by accounting for the expected occlusion through the occupancy. And given this expected feature along a ray, we can then render the foreground, we can render the pixels as well as infer the foreground mask. And at a very high level, there's this differentiable rendering process that really uses the predicted occupancies in a geometrically meaningful way to render the predicted image. And given this rendering process, we can just say that the foreground mask and the RGB image prediction that we make should be as close as possible to the original input image that we had, which was sort of the self-consistency loss that I was talking about earlier. And the second objective that we enforce is, again, that given an arbitrary viewpoint v prime, which has nothing to do with the predicted viewpoint for this particular image, the rendering that we get should just appear realistic, where the realism is determined by simultaneously training a discriminator D that is trying to say that the real images are real and these rendered images are fake, whereas our network is, of course, trying to generate 3D predictions such that their renderings look as real as possible. And essentially just using these two allows us to learn 3D, and I just want to show some oblations emphasizing the importance of these terms. So for example, if we don't use this geometry-informed ray tracing process, as for instance some prior work like Hologan does, things don't really work very well. And incorporating appearance, as in the RGB pixels, as opposed to just using shape or silhouette cues, is also critical in getting good results, or sort of better results, which is what I show here. And then we have actually just some very simple instance level specialization process where, again, I'll skip some of the details, but at a very high level, we convert the occupancy predicted to a mesh and transform the voxel features onto mesh features, and then just optimize it to better match the details in the visible regions of the input while enforcing some symmetry constraints and some visibility map. But this is essentially just some simple optimization where we optimize the mesh to better match the texture and the shape of the original input. And this lets us get some reasonable results on categories like birds. And again, I'd like to emphasize that this reconstruction has been learned using nothing but a few 100 to 1,000 images of birds with foreground segmentation masks, without requiring any templates, without requiring any key points, without requiring camera poses, and sort of works on some other categories as well. So quadrupeds can capture some larger variation with some methods that rely on templates cannot. For example, different types of chairs, one with 4 legs or one with rotating legs, but sort of more interestingly and sort of more closer to the goal that I was initially mentioning, it actually lets us obtain at least coarse reconstructions across a very broad set of categories. So for example, on things like laptops, shoes, bagels, hats, and sort of many other categories like guitars, and sort of cups, etc. And in our paper, we showed that this system, using just images from open images, can actually learn meaningful 3D prediction on something around 50 to 100 object categories, using just these image collections with approximate foreground masks that have been used, that have been obtained by using an off-the-shelf system. And sort of while we have trained this model to only reconstruct isolated objects in a category-specific way, we can just combine it with detection systems to at least infer coarse 3D structure of a lot of the objects present in more complicated images, such as from MS Coco, where we can lift some of the food items present here to 3D representations, and or even get some coarse 3D for the cup, or do similar things for the indoor scenes in this particular image. But sort of one aspect that I want to really highlight about our approach, and in fact, a lot of the other unsupervised 3D learning approaches, is that they really learn category-specific models. So in our particular approach, given an image collection with just foreground masks and many images, we learned this specific category-specific reconstruction model that could then infer 3D for a new object of this category. And so given images of birds, we learn a bird-specific reconstruction model. Given images of cars, we learn sort of a car-specific reconstruction model. Given images of deers, we learn a different model that is specific to this particular category, and so on. And given images of hats, we learn a separate model that's only specific to hats. And to some extent, this category-specific learning is required because in the absence of supervision, we need some way of regularizing learning and to prevent sort of arbitrary or degenerate solutions. And while this is good, it's also not ideal because there's no sharing across these models, and we need a lot of these clever regularizers such as adversarial priors or templates to constrain training, because we are training each of these models from scratch. And of course, they're not very expressive because each model is trained independently on a category and really cannot benefit from the common structure across objects. For example, vases are round, and perhaps hats also have some structure in them that is round, and so a common model might perhaps reconstruct them better. And so in sort of recent work that I'll very briefly gloss over, we just looked at these assumptions as to whether we really need to train things from scratch and independently. And we actually just had two very simple ideas to improve the process of self-training. One is, instead of starting from scratch, we can have a model that starts from some pre-training on synthetic 3D data. And even if the synthetic 3D data is on a very limited set of categories that are actually rather different from, let's say, animals that we want to self-train on, this is actually sufficient to simplify the pre-training process and actually removes the need for any regularizers. And once we have done that, we can also just unify all the reconstructions that we have learned into a common model. And that A, makes the inference far more efficient, and B, also improves the performance because this allows us to do some sort of sharing across categories, and sort of gives us a better model to start when we are self-training on new image collections. And just to sort of highlight some results, given these images from a diverse and arbitrary set of categories, the work that I was talking about earlier, the shelf supervised mesh prediction from the earlier CVPR, does an okay job at reconstructing these objects, but has some artifacts and not very precise structures. For example, if we look at how it's reconstructing the purse, it doesn't do a very good job because it has been trained from scratch, given just a few hundred images of purses. But I mean, that said, this is still better than the state-of-the-art systems that existed at that point, which could use similar supervision. And just training on synthetic data and applying that model, of course, doesn't work because it has not seen these diverse set of categories. But if we just use the synthetic trained model to then do self-training on new categories, that gives us pretty accurate results. And in fact, if we have a model, sort of a final model that is distilling all the category-specific models into a singular model, that in some sense actually even improves reconstructions a bit. And of course, gives us a single model that is reconstructing 3D across all these different categories at the end. And I'm actually just going to skip some of the results to just highlight the trends that we saw earlier, but show you some more images where, again, all of these reconstructions are obtained using a single model that is trained over 150 categories and can reconstruct, at least coarsely, the 3D structure across these different objects. And all it has been trained on in terms of real images are just these image collections with just foreground segmentations. And sort of it works reasonably well across a very broad set of categories, such as this drill, or sort of a rocket, or shoes, and of course, sort of more common things that we saw earlier, such as birds, etc., or shapes like balloons, laptops, and so on. And so, yeah, I think maybe this is a good time for a very brief break. I don't know if Tianfan or Qixing know if there are questions from folks online that we should address first before moving on, or I'm happy to also move
on. We address all the questions in the end. Okay. In fact, I already have a bunch of questions, but maybe it would be good to leave that to the panel discussion. Okay.
Yeah. Okay, sure. Yeah, that sounds good. So to just look back, the work that I talked about, also the couple of works that I talked about, were just pushing the boundary in terms of single view reconstruction of how many objects, or trying to push the boundary from going to a few tens of objective categories to maybe at least 100 or a couple of hundred object categories using these image collections as supervisory signal. But so the next work that I want to talk about takes an orthogonal approach and looks at whether we can relax the requirement of these multi-view reconstruction systems that really rely on these hundreds of images to learn 3D inference, and whether we can do this sort of 3D inference using a far smaller set of images. And in particular, this part of the talk is based on this work called Neural Reflectance Surfaces, which is about to appear in NeurIPS, and I think the poster presentation is next Tuesday morning, so please go and talk to Jason, who really did all the hard work for this then. And the setup that we are interested in is to some extent motivated by this marketplace setting, where someone who wants to, let's say, sell their car would naturally upload a few images of the object that they want to sell. So for example, for this particular car, the user uploaded 8 images on Craigslist. And these 8 images show the car from diverse perspectives, but these are, of course, a far cry from the hundreds of images that some of the recent multi-view reconstruction approaches would require. And given just these 8 images, we want to be able to infer the 3D for this particular object. And I really want to highlight this is a very challenging setup, because classical systems that estimate, let's say, even just camera pose or coarse 3D structure catastrophically fail on these kind of sequences, because there aren't enough images to provide robust matching. And this sparse view reconstruction has a wide baseline, very low overlap across these images, and some of the classical pose estimation systems cannot really handle these well. In fact, this result that I'm showing here from Colmap is not from this specific sequence, but from a sequence that had even more viewpoints, but is representative of the typical failure cases. And in fact, I think across 10 or 15 sequences that Jason tried, this was perhaps the best Colmap sequence that we could get. And this still has, while it did some registration, it's sort of false, and it only has this planar surface and really cannot infer the camera poses or even coarse 3D structure, which is something that, again, some of the recent multi-view reconstruction approaches almost take for granted. And so the sparse view reconstruction setting, I hope I've just convinced you that this is a slightly challenging setup. But of course, it's a very relevant setup because of applications such as in marketplace settings, or even in where, for instance, we want to be able to reconstruct 3D given just these 8 images. And in particular, what our work does is it also uses 2D segmentation masks that can be obtained using, again, off-the-shelf systems such as Mask CNN, and an initial shape of the object. And this particular shape, as you might notice, is just a very generic sedan-like car and is actually quite far off from this particular truck that we're interested in reconstructing. But just some initial shape to sort of bootstrap the optimization suffices. And in conjunction, we just rely on some recognition-based off-the-shelf camera poses, which are, again, not as precise as we typically get from Colmap when Colmap works. These often have sort of up to 30 or 40-degree pose error, and we need to be able to account for that in the learning process. But given these 2D images with off-the-shelf segmentation masks and this coarse initial mesh and off-the-shelf pose estimates, our approach looks at being able to reconstruct in 3D the shape of this particular object. And it's not just limited to cars. So the same approach really applies to more generic objects as well. So for example, this is a particular desktop captured in one of the CMU rooms where I think Jason just walked around and took 8 random images, and those were sufficient to recover a rather detailed and accurate 3D model of this particular object. And so, not only can it help us reconstruct objects in these marketplace settings, it's also very useful for this casual capture setting where someone who wants to reconstruct a new object can just walk around, take a small number of images, and get a reliable 3D pose estimate, sort of 3D shape from these. And just to sort of convince you that this approach really does work at scale, here's sort of a teaser of some of the results that we're able to get at the end, where the same system with the same initial shape can reconstruct over 200 cars from the Craigslist dataset and can capture rather different shapes. And maybe I'll display this again. For example, all these 4 shapes that we're seeing here are subtly different from each other, and so are all the other 200 that are there in this video. And our approach is able to capture both the shape and appearance of all of these. And sort of before going into this approach, I'm sure the setup that I talked about, being able to reconstruct accurate 3D while modeling appearance, reminds you of the seminal work of, for instance, Nerf, which also tackles a similar task, albeit with more number of input views. And really, I'm sure all of us have seen some results of these kind, where it's able to very precisely and accurately model both the geometry and appearance of these rather complicated objects. And the reason for the success of these neural volumetric representations is their expressivity. So for instance, Nerf represents the 3D structure as almost an unconstrained geometry and appearance model, where at each point we model a free-form density, and at each point we model a direction-dependent appearance. And this really allows a very expressive model, which, given these hundreds of images, can fit really well to the data and capture the shape and appearance of a new object very well. Unfortunately, this expressivity is also the reason for its downfall when we are trying to reconstruct objects given just a sparse set of views with approximate cameras. And so here I'm showing results that we get from sort of a Nerf plus approach, where we add a lot of bells and whistles to make it optimally use masks and approximate cameras, etc. But even despite that, we see that the geometry and appearance that it captures isn't quite as accurate, and there are some floating structures. The geometry is obviously off, the appearance is not great. And this is because the Nerf representation is sort of severely under constrained, and it does not do well in the face of limited amount of training data. And sort of our key insight was just to constrain the space of possible solutions based on what we know about the world. And sort of the first idea that we had is most of the objects that we are interested in reconstructing have well-defined surfaces. So instead of a arbitrary volumetric representation, we pursue sort of a more well-defined closed surface-based representation. And similarly for view-dependent effects, instead of allowing arbitrary view-dependent effects, we really use the insights from computer graphics to constrain the space of possible view dependence. And I'll maybe also just gloss over some of the details, but the shape representation that we use is essentially a neurally deformed sphere. And this gives us some nice properties, that it's a watertight surface, and similar to neural radiance fields, we use position encodings to allow capturing some high-level details, such as the side view mirrors. And sort of the more interesting aspect of the work, I'd argue, is how we model view-dependent effects. So when modeling view-dependent effects, the question that we are interested in answering is, given a point X and a camera that is in view direction V from point X, what is the light that would outgo from the point X to direction V? And there's this sort of very famous and classical surface rendering equation that is well known in computer graphics, which answers this question by simply integrating all the light that is incident to the point X and using the BRDF, which is sort of a material property, to integrate this incoming light and compute how much of it goes back in the direction V. And so while this is something that's just very well known in classical, the radiance field solution, the neural radiance field solution, is to sort of ignore this knowledge about surface rendering and instead say that we can use just a neural network to model this outgoing light from a particular point X in a direction V. And sort of while this is again a very expressive representation, it fails to generalize in the regime of low amount of training data. And instead, our solution is to learn neural but constrained models of the lighting in BRDF and still use surface rendering equations to model view-dependent effects. And sort of more concretely, we make a couple of simplifying assumptions, which is first, we assume that the lighting can be modeled as an environment map. So this technically assumes that the lights are all infinitely far away and sort of corresponds to an outdoor lighting setting where there's the sky which is giving some light, but there are no very nearby light sources. And the second assumption, and again, this light can be modeled as a neural network that maps, that predicts how much light is incoming from any direction, which is modeled by a point on a sphere. And the second assumption that we make is we constrain the allowed BRDF, and instead of allowing a free-form BRDF, use sort of a form reflection model. And to improve this, you can perhaps choose your own favorite model. But essentially, this allows us to decompose this view-dependent appearance into sort of a view-agnostic effect that depends on the surface texture at that point, which again can be neurally represented, and some view-dependent specular effects, which can be captured by a very small number of low-dimensional parameters, which I'll maybe show in a bit. And given this representation of view-dependent effects, we can render a predicted view using the predictions from NERSC. And sort of more concretely, our NERSC representation predicts the shape of an object, the surface texture of the object, and the lighting in this particular scene, and all of these are modeled as neural networks which map points on a sphere to the corresponding scalars or vectors. And given these, we can compute sort of the geometry or the surface normals from this particular camera viewpoint, and using the surface rendering equations, which I'm sort of glossing over, compute how the output radiance or the per pixel appearance looks like this particular LO. And this sort of allows us to still generate view-dependent effects that are induced by the specular lighting point image that you see in the middle. And once we have this rendering process, the learning pipeline is actually just very simple and sort of, again, very standard. We just optimize all these parameters to simply match the input images as best as possible. So more concretely, we optimize all the neural networks for representing shape, texture, lighting, and also the low-level specularity parameters, sort of alpha and k, which I didn't go into too much, and also optimize the camera parameters because they're only approximate, such that the reconstructions match the set of input images as closely as possible. And we use a couple of off-the-shelf systems to initialize the shape and the poses, and I'm going to skip that in a bit. But essentially, just here are some results to show that we are able to capture diverse shapes using, again, the same initialization across all these three instances, and are also able to model some view-dependent effects, which we visualize in the right image, which is showing the view-dependent effects with sort of a mean texture image. And yeah, again, sort of going back to some of these results, where we really see that our system is capable of reconstructing a very broad set of objects, such as these diverse cars. And a lot of the results we are showing are on cars because it's easy to collect data of these from marketplace settings, but in a bit, I'll also go into sort of more generic objects. But before moving on to those results, I want to very briefly touch upon evaluation, because I think this is sort of a slightly subtle point that is missed in a lot of the recent multi-view reconstruction novel view synthesis approaches, where the typical paradigm for evaluation is to say that we have input images, and given these input images, we learn some sort of black box 3D representation. This can be sort of your favorite model like Nerf or IDR, or sort of our approach. And given this 3D representation, we have a held out target image, and we want to check whether the rendering of this 3D representation matches this held out target image. And while this is a reasonable evaluation protocol, what this implicitly assumes is that we know precisely the ground truth cameras for both the input images, and more importantly, know the precise camera for the query image, because we say that this target image should be synthesized from a viewpoint of 30 degrees elevation and 20 degree azimuth, for example. And this is really a challenge because we don't have precise cameras in realistic sort of in the wild sparse view reconstruction setups, and we kind of very rarely will. And so we also need a way of evaluating this 3D reconstruction while accounting for the fact that we don't have precise cameras even at testing. And so to account for this, we actually designed two evaluation protocols, where the first protocol included the first author Jason manually defining sort of pseudo ground truth cameras for our evaluation sequences. But the second protocol, which I really want to emphasize that people should be adapting a bit more, is we learn 3D representations while allowing camera optimization, and also allow some camera optimization during evaluation, because the cameras that we have might be imperfect. And I think I might skip the details of the evaluation and sort of numbers to show more results, but we do show results on both these evaluation setups. And we show that our approach, at least in the sparse view reconstruction setting, is sort of clearly better than some of the earlier approaches, which work great when we have hundreds of views, but fail to work very well in the sparse view reconstruction setup. But sort of more interestingly, this also holds up in this other evaluation protocol, which I'd argue is a bit more realistic. And I think, yeah, just here is some more comparative results where we're showing our approach on the left to some alternate approaches, which either use volumetric representations or SDF representations, but more importantly, don't really constrain the view-dependent effects, whereas our approach does, and that leads to improvements both in the geometry and the view-dependent prediction. And of course, the same approach also works on more generic objects, where maybe as a homage to Pittsburgh, we reconstructed the Heinz ketchup bottle or some other sort of PlayStation controller, again, given just 6 to 8 images of each of these objects, and a very coarse initialization of in just the form of a cuboid, we're able to reconstruct a pretty accurate 3D shape for all of these objects. And of course, I'm not showing, but we also assume foreground masks for these systems, either using GrabCut or some off-the-shelf systems. And maybe just a couple more results before I wrap up. And again, all of these objects can be reconstructed given just a small set of images and with very coarse pose initializations, sort of with often 30 degree or higher error. And yeah, just sort of looking back, I hope if there's one thing you want to take away from the talk today, I hope it's sort of this landscape, where ideally we want to strive towards systems that really, really work on tens of thousands of object categories and are very easy to use. And while we are unfortunately not quite there yet, today I showed 2 systems which either reduce the number of viewpoints and can still work on rather generic objects, or one system which pushes the boundary of how many categories single view reconstruction methods can tackle. And yeah, I'm happy to take questions.
Okay, thanks, Shubham, for the wonderful talk.
Very nice
so
talk.
Now we move to the panel discussion session. So I do have a lot of questions, but so we have a panelist, Tianfang Xue, again from Google Research.
Yeah.
So Tianfang, you has been working in this space, right? So so basically the panel discussion has 2 sessions. One is specific to the talk. The second one is that we want to discuss general topics in this broader field of reconstruction from images, right? So in the deep learning era. Okay, so Tianfang, maybe you can start with some of the questions that are related to the talk.
Yeah. Let me start with some simple things first. First of all, this is really nice one. The nice talk. I really enjoyed listening to the idea. I have like this like a scale from the easiest to the hardest 3D reconstruction. More specific for general, this is very impressive. So just one quick question about the last part you're talking about. Like you're talking about this this evaluation problems. I think this is really important. That like there's no precise camera position. There's actually one related point is that sometimes it's also hard to get a ground truth or any kind of a ground truth nice reconstruction or lighting environment of the scene. Like say, if you go back to one of the slides you showed there, the reconstructed images actually looks pretty nice, but it still looks different from the ground truth. And I think one of the reasons is the lighting is slightly different. And personally, I feel there's very, very challenging to really recover the very ground truth environment map of the scene. So do you think there's any way to make the evaluation of kind of a more robust to the lighting effects here?
Yeah, so I think this is a very good point. And I remember having this discussion in CVPR in some panel as well. And one great suggestion that someone had was to essentially take images of the same scene under a few lighting conditions. And then I think we do have some systems which can disentangle sort of if we are imaging under different lighting conditions, we can disentangle sort of the true underlying texture versus the light dependent effects. And maybe some small controlled captures like that would be a good benchmark. That said, one thing I personally really care about is being able to evaluate it in the wild settings where there are more challenging and natural viewpoints. And these two goals are a bit orthogonal, and we don't quite have very good answers on how to get evaluation in the wild setting.
I don't have a good answer to that either. I mean, I'm also wondering whether there's just really thinking about like saying if there's a way we can relighting a bit about the ground truth itself to make it have a more variation or the other way around. Is there a better loss function that kind of more or less ignoring the lighting effect when comparing the difference between the ground truth and
the one issue with using a specific loss function is that then a method can always train to optimize that loss function.
So step 6, we're talking about like the lighting effect. Actually, there's another related question for your first part of the talk is that you have this very nice rendering engine giving a 3D or volumetric representation to generate new images and render back to compare with the input. And do you think the lighting effect may also make training harder? Because if the image is a long version, then it's pretty. I mean, this volumetric representation is pretty good. But if there's like say strong non-long version effect, like the car example you shown, it's actually quite challenging for any 3D reconstruction algorithm because of the strong lighting effect and also the reflection. Would that make the rendering harder?
Yeah, so I think it's a great question. And when we are doing this single view reconstruction and learning from image collections, I think lighting is a challenge, but I feel there are so many other challenges in that setting that lighting just doesn't show up very prominently, because if we just have a single view, in some sense, we could have a predicted texture sort of just absorb almost the lighting effects. And, I've typically seen that the networks do kind of learn to do that. And there, I think really the goal is we just want systems that get pretty accurate coarse reconstructions. I don't think from single view and learning it from image collections, we'll get systems that very precisely get amazing texture and can disentangle things like that. So I think as long as modeling appearance gives us some signal for improving geometry, it's still useful to do that, even though we can't explicitly factor out lighting.
I think like like learning a 3D geometry in the wild by itself is a really challenging problem. Like even like learning the rough 3D, like the rough 3D floppy like shape by itself is really challenging problem by itself. And related to that, I also like the idea, like saying that you have this kind of like first have a rough reconstruction, and there's a second part is like kind of instance level reconstruction, which kind of feel like reminds me how like a human perceive the 3D world. One example is like saying that if I look at like say a car, I can definitely immediately recognize, okay, what's the size, how big is the car, how long is the car. But if I ask myself to say using 3D software to make a car like what is shown on the image on the screen, it's very challenging. I cannot do it. It's just like you can only get a disbobulated result. So this actually kind of reminds me that like maybe there's actually two separate problems here. One is kind of general 3D representation understanding of what do you do right now, and there's more probably a second part, like given this image, let's try spend a lot of computer resources, try to make this one particular 3D geometry really nailed up to this image.
Yeah, I mean, I think that's a very good point, and it actually reminds me of something my PhD advisor Jitendra used to constantly say, which is when humans predict 3D or sort of understand 3D, there are aspects of prediction where we are guessing structure that we have not exactly seen, and there are aspects of measurement because you do move around a bit and get very precise geometric measurements for some aspects. And in human systems, both of these things keep happening together and synchronously. In what we have done so far in the vision community, approaches either look at prediction or look at incorporating measurements, and a system that can do all of these things together coherently is still part of.
Okay, so thanks Stefan for the questions. Okay, thanks Shubham for the answer. So I have two or three questions related to the talk. So the first question I have is that thinking about, for example, this can be constructing the wild settings, right? So I think the view-dependent effects making the problem very challenging. Okay, and so one way is to, as you mentioned in your talk, right, is to use rendering models, right, depending how good how complex the model is, right? So we really want to model, right, this kind of view-dependent effects. So I don't know if people have tried this. Have you thought about, for example, we can use image translation techniques, okay? So for example, like given the input images, we can train, some image transformer to factor out the view dependent effects, right? This kind of reflections and so on, right? So maybe one can like have a synthetic data set, right? So where we don't have those kind of view dependent effects, we train a transformation. Then once we factor out this kind of view dependent effect, we can do you think, first of all, do you think this is plausible? Okay, and right. So once we factor out view-dependent effects, then we can reconstruct from those images. Do you think this is possible, or maybe may not work? Yeah.
I mean, if we can magically factor out view-dependent effects, I think that would be great. I'm just worried that this being able to do this in more general settings, so like a system that, given all these 4 images that you're seeing here, can factor out view-dependent effects. I think this is a very hard problem, and I'm worried we may be solving like a harder intermediate problem for our actual.
Okay, yeah. So I was just wondering, for example, if it's precisely modeling the view dependent effects is too complex, maybe is like the factoring out, removing those, right? If this is possible, right? So then we don't need to go. Yeah. Just okay. So this is first question. The second question is that it's also general in the sense that, for example, if we think about reconstruction, right? So if we have a sufficient shapes, right? So in each categories, right? So of course they're different from the real world objects, because the man-made objects, right, modeled by humans are not the exact, but still they may provide some priors, like the local priors, like global priors that one can utilize to regularize the reconstruction, right? So do you think this is something that could be potentially useful?
Yeah, so in fact, this insight is exactly what we used in sort of the extension of the first part of the talk, which is instead of training these category-specific models from scratch, let's use some 3D data that we do have to bootstrap training. And this helps even if the new categories that we are interested in are kind of different, like quadrupeds. Now, of course, we haven't used that yet for the sparse Yuri construction setting, but I think that is a very fruitful avenue of exploration because in some sense, the setup here and in Nerf, etc., is that here are K images where maybe K is 100 in Nerf and K is 8 for us, but this is all you know about the universe and then reconstruct the object. And in some sense, this is a slightly made up problem because we do have experience with other objects. So a more realistic setting is we have seen thousands of objects. Given that, we want to reconstruct this new object from maybe one or small set of images. Now what can we do? And I think, yeah, this is a very fruitful direction to look into.
Yeah. Okay, the final question related to this particular, what they talk about is that, so most of the objects, right, so either man-made or this kind of organic shapes, they have this various levels of symmetries, right? So refraction symmetry, or maybe part of the shape has symmetries, right? So partial. Do you think, I mean, of course, detecting those symmetries from images, like most of the symmetries are not exact. Okay, it's challenging, but do you think this is something that can be incorporated, or maybe it's just too difficult, right, to do?
Yeah, I mean, I think I keep going back and forth on this. If you had asked me this in my third, fourth years of grad school, the answer would have been like an emphatic yes, that we should explicitly detect symmetry and sort of almost use it wherever feasible. More recently, I think my viewpoint has become that if we have seen some models, whatever prior we are learning over them, the statistical prior should hopefully just implicitly understand that there are things like symmetry and should be able to just use it without us explicitly having to say it. And yeah, I don't have a very good answer for it. I could kind of argue both sides of it.
Yeah, I agree with that. I think that statistical model, shape models, to some extent, they captures the symmetries, right? To some extent, right? So that has to be incorporated in the model.
Okay. Can I jump into this question?
Okay.
One quick follow. So actually, I'm wondering whether, like, I really like the idea of symmetry. I'm wondering, like, instead of like saying explicitly detect those symmetry, is there a way we can build a network in the way that inexplicitly prefers some symmetric representation? For example, I'm like saying that right now we all use convolution networks. Convolution by itself, like saying that we apply the same kind of operation in the repetitive locations. Whether by using convolutional structures, it explicitly already incorporates some symmetric information we don't explore yet. Whether we can explore other network structure that maybe, say, incorporate some like a left and right symmetry or other kind of symmetric information.
Yeah, I think it's a fundamental challenging for them. So what I do know, for example, in very specific cases like this kind of implicit functions, right? If all the shapes have reflection symmetry, and suppose all the shapes are already oriented, okay? Then generally the shapes tend to preserve the reflection symmetry for the new instances, right? But this is very specific. For example, if you think about this kind of rotation symmetries of the like the chairs of wheels, I don't know whether this kind of implicit representations can capture that. But on the other hand, they're specific, like this kind of so this kind of pod-based model. Shubham actually did some works in that direction, very early works on that, right? So people have been explicitly encoding the symmetries into a generative model, but still that requires supervision. Okay, we annotate the symmetries, which I think is very challenging to annotate. Okay, so from my personal perspective, learning models from scratch so that the generative models automatically preserve the symmetries without much this kind of explicit supervision is actually an open problem. I don't know whether you guys agree with that. Yeah. Okay. Okay. Okay, so let's move to the second session of the panel discussion is about thinking about this kind of big picture, okay, big picture, right? So this kind of a new 3D reconstruction. So usually there are two aspects of this, okay? So one aspect is that if you think about, let's draw an analogy for example, to image understanding, right? Which we have was well-known use systems in industry. So there are two aspects of it. One is data, right? For example, in image understanding, right, we do need very good training data at scale, right? So at least for example, this kind of foundation models, right, the transformers. Another is the architecture perspective, right? So we want to have better models, right, given specific training data. So I want to ask, for example, let's start with Shubham, right? So which one in this 3D space do you think is more important to push forward? So data and models, okay?
Yeah, I mean, sort of a very biased answer because I do believe in the power of structure and geometry. I would say that models which more closely tie what we are predicting, with the geometric nature of the 3D inference task and more closely tie it with images are going to be pretty important. So in that sense, I think models which have the right geometric inductive biases, I think are probably going to be more useful, especially because I think it may be that if we are interested even in reconstructing sort of long tail categories for which we will probably not really have thousands of 3D models, at least my belief is having these more structured models will let us generalize better to this natural long tail of objects. Whereas just reliance on a lot of data will probably let us do a very good job on some of the more common categories.
Okay, so I do agree, right? So we will have a more specific discussion on this kind of representations that generalize very well to thousands of categories. I think this is fundamentally challenging, right? We will talk about compositional stuff over there, okay? I do agree this is something very important. So, okay, so let's move, thanks Shubham for the comments, and let's move to Tianfang. So you're working like at least at the intersection of this kind of academia research, right, and industry. From the industrial perspective, right, if we really want to scale up this kind of this visual 3D perception to thousands of categories, right, or in the future, right, to have this kind of working systems. So which one is, for having a concrete solution perspective, which one is more important, like having a very high quality data or having this kind of better models?
So actually, I have to say both. What I would like to say is that I find, like, at least even in industry, it's almost impossible saying that we just scale the number of 3D data to the scale, like say ImageNet, because capturing 3D data is really, really time consuming. Even even say in Google, like this is not like getting a large set of 3D data set in the scale of ImageNet is very, very challenging. So I think there's something we need to do smart in the algorithm side to better utilize the data we have. So one thing I think is the better way to combine the 3D data we have as well as there's tons of 2D images, like I forgot what's the exact numbers. I think it's hundreds of millions of images being uploaded to the website, and all this can be much more beneficial than just say we capture 3D data. So I think something Shubham is currently trying to push, like saying that if we have a large set of 2D images with not lot of supervision on the 3D information, where there's kind of self-learning to get some 3D geometry out of 2D images. I think that's like, even from an industry point of view, that's probably the most feasible solution, because we really want to nail down those long tail long tail categories, not only focus on few categories. This is the only possible solutions. from my perspective. So I would say both. In the main so that we need a better algorithm to get a better data.
Okay.
Yeah.
Okay. So this brings to a relevant question that we have not discussed so far, right? So I think from machine learning perspective, we have right. So we have this kind of multitask learning, right? So what it really means that, for example, 3D reconstruction. I think Shubham at the very beginning mentioned that, right? 3D reconstruction is connects to many other relevant tasks, right? So for example, the key point may provide some regularization and so on, right? So maybe we can open the discussion to, for example, like if we think about what are the tasks that can benefit 3D reconstruction, what are they, right? So for example, some of those tasks may have label data that can be partial, right? So can be transformed to 3D reconstruction, right? So maybe we start with Shubham again, then we move to Tianfang. Okay.
Yeah, I mean, so I think one of the very fundamental tasks is that of estimating some sort of correspondence or similarity. And like, well, okay, it's not a very surprising answer given that's what, let's say, all the classical multi-view reconstruction approaches relied on. But even at a category level, if we can infer that, you know, this part of this chair sort of looks semantically or functionally similar to this part of this other chair, it's maybe a slight generalization of key points. I mean, I don't like key points because sometimes they're hard to define for generic objects. If you see, for instance, this particular pointer, it's just hard to define what key points even mean for this. So correspondence is maybe a slight generalization. So correspondence captures a bit more semantic aspects in my mind. And then there are some more geometric or graphics-based aspects, which you guys both touched on, which is being able to factor out some view-dependent effects to from the intrinsic surface properties, or just trying to figure out surface properties for whatever is visible. So maybe that also includes things like normals, etc., which is maybe a more geometric but local task.
Okay, thanks for Shubham for the answers. Like, let's move to Tianfang. So what kind of tasks do you think can potentially beneficial 3D reconstruction, right? Or vice versa?
Yeah, I just want to share a slightly different perspective. So I think if we can really get a very good 3D reconstruction, can benefit a lot. One particular area I think is really interesting is to generate a lot of synthetic data for training. Like for example, like for people who work like I'm working a lot with cameras, like saying that if I want to generate some training data for cameras, like say I have one camera and I want to generate another images captured by different cameras or camera array, or say I want to generate a defocus image, all this requires some 3D information. Or like saying I want to generate a sequence, like a video sequence from a static image, so I can generate like a flying camera sequence. All this kind of requires some 3D information, and if we can have a better reconstruction of the real world images, then we can generate much more synthetic images in the way that we want. That can benefit a lot of other tasks. So I think a very strong synthetic, like a 3D reconstruction and plus some synthetic engines, that could be beneficial for a lot of cases. Another good example is like saying self-driving cars. Like people like capture a lot of images on the street. But if there's some synthetic engine saying that we can synthetic what our street work like, then this can generate tons of new training data for those tasks. We don't need to really run the cars on the street. We don't really take any risk for cars being hit by hit some person. So I think if we really can nail down the 3D construction, that can actually provide us tons of more training data for many works. We're like particularly for those tasks, we are suffering from the data shortage problems. Yeah.
Okay, I agree, right? So I think in that sense, so basically Tianfang's comments that I think 3D reconstruction, if we really can do this at scale, right, it can benefit many other tasks, right? So in that sense, I think that what Shubham has been doing, right, not just geometry, but also appearance, right? So that's very important. Okay, so let's move to the last, this kind of problem is related to, of course, to generalizing to like thousands of tens of thousands of categories, right? So what representation, okay, what representation, and also what are the fundamental challenges here, okay? Maybe with this time we start with Tim Huang, then we move to Shubham, okay?
Okay, yeah, sure. Yeah, I think this is in general very challenging problem. Like I think there's a many representation people use for 3D construction. There's a voxel representation. I think the voxel is the most friendly representation for deep neural networks because it's basically a 3D matrix. And there's a mesh representation. Then there comes from a question how to integrate it with the current neural network structures. And there's also like say neural radiance fields or like a multi-layer planes as representative of 3D words. So I think each one of them has a pros and cons, and having like saying that getting a good balance between the representation power and like the way how to connect with the neural networks is very important. From a representation point of view, I think mesh is definitely the most powerful one. I mean, like most powerful and compact one, but also it's the one that's the least compatible with the neural networks. Well, on the other side, the grid representation is the best one we can integrate into current neural network structures. But like from graphics point of view, this is actually the worst representation we can use for 3D geometry. So I think finding a good balance between these two might be like a kind of a long-term research. And also, I think it could be the case that it's some hybrid. There will be some hybrid model saying that in the very coarse scales we use some grid-like representation, and in the refined scales, kind of like if you really want to nail down some details of 3D geometry, we can use mesh, we can use some radiance field representation, or like say if we want some kind of like a lighting effect, we can use that. So I think some hybrid model might be another solution for this problem.
Okay, I actually, so let me summarize. I fully agree with Stefan's comments that I think generalizing from, for example, tens of categories with label to thousands of the categories, right? It really depends on what kind of generalization we want, right? If we want the compositional generalization, then this kind of pod-based is very important, right? But if we really want this kind of front-grained details, right, generalization, right? Many of the details may already present, right, in those kind of tens of thousands of maybe 100 categories with labels, right? Then we need other representations for this kind of generalization, right? So I fully agree. Now let's move to Shubham for this comment and also concludes today's seminar. Okay, share your thoughts on.
I mean, I want to address a slightly orthogonal point in the generalization to many categories, which is while we are framing this in terms of categories just to express the scope of the task, I think I've more recently sort of adopted the framework that the system should not really care about categories. It should just care about here's an object and here it's 3D. In the sense, we are making these kind of boundaries in categories that, okay, here are things that I'm going to call chairs and I'm going to learn their prediction together. And that helps a bit because for some categories, the shapes do share a commonality. But for a lot of other, what we call categories, things are more functional and the shapes are just a lot more arbitrary. So I think to really have a system that generalizes, we should have a system that doesn't care about the category of the object. It should just be something that goes from an image to a 3D representation and is sort of a unified system that kind of deals with all sorts of generic objects. And I think that has a better hope of generalization to arbitrary objects than something that is first taking a category route to predict 3D.
Yeah. Okay, I also agree, right? If we really understand this kind of inter-category variations, right? If we understand this, then that definitely help to generalize to new categories. Okay. Okay. So we have a wonderful. This can have a wonderful panel discussion. And thanks, Shubham, for the wonderful talk. And thanks, Tim for joining us, sharing all your thoughts on in this space of 3D reconstruction. So this concludes this week's 3D Jimmy seminar series. Thanks everyone for attention. See you next week. Okay.
Thank you.
Thanks.
Thanks for
Okay.
Thanks.
Okay. Bye.